Perched above Cusco is where Inca engineering, logistics, and artistry converge into some of the finest stonework on Earth. Its enormous polygonal blocks fit so tightly that joints can be hairline thin without mortar. How do they do it? The sheer scale of the site is breathtaking. Many blocks weigh tens of tons, the largest are over 100 tons, yet the joints remain astonishingly tight and complex. They are so precise that even today we can't easily fit a sheet of paper between the stones. And the faces are incredibly smooth, too. In Quechua, Sacsayhuaman is often rendered as satisfied falcon, a fitting name for a site that crowns the city below. What makes the fit so extraordinary? First, there's monumental scale. Many blocks weigh tens of tons. The largest are over 100 tons, yet the joints remain astonishingly tight and complex. Polygonal geometry. Stones often have 6 to 12 plus sides, interlocking in 3 dimensions like a 3D puzzle. This distributes loads and resists sliding, no mortar. The precision comes from sculpting each stone to mate with its neighbors. Faces are slightly convex with finely pegged, burnished contact lines. Seismic intelligence. Inca builders anticipated earthquakes. Walls have an inward batter, a slight lean, variable block sizes, and irregular joints that dissipate earthquake energy. The 1950 Cusco quake toppled many colonial buildings, but these Inca walls held zigzag ramparts. 3 long serrated terraces form the complex's iconic profile. In local tradition, they evoke the puma's teeth in a city said to be laid out in a puma shape. How the Inca likely did it: evidence-based reconstruction. First, quarrying and selection. Stones were sourced from nearby quarries and from major andesite sources in the Cusco region. Surfaces show telltale percussion marks from hard stone hammers. Blocks were roughed out at the quarry to reduce weight before transport. Transport and staging. With no draft animals or wheeled heavy transport, teams used ropes, levers, sledges, and earthen ramps, coordinating large labor forces along prepared routes, shaping and fitting. Masons pegged high spots using dolerite or andesite hammerstones, then test fit stones repeatedly. Scribing with pigments, charcoal or ochre, likely marked contact points. Peck, polish, test cycles continued until the joint was tight. Subtle convex faces and beveled edges protect the joint lines while keeping contact tight where it counts. Wall construction. Double-faced walls with a compacted rubble core excellent for drainage and energy dispersion. Trapezoidal openings and an inward wall batter enhance stability. Integrated drainage channels mitigate water pressure behind the walls. Why it works so well? Mechanical interlock. Multi-sided stones, L-shaped joints, and vertical keys make it hard for blocks to move independently. Energy dissipation. Irregular joints and varied block sizes break up resonance during quakes. Redundancy. Even if one contact loosens, others take the load like a 3D puzzle designed to flex, not fail. When was it built and what was its purpose? It was built largely in the 15th, early 16th centuries under Pachacati and his successors. It functioned as both a formidable defensive complex and a ceremonial precinct overlooking the Inca capital. It's an architectural statement of state power and sacred landscape design. Myths and realities. Razor blade joints. The fit is extraordinarily tight at key contacts, but not every joint is hairline along its entire length. Nor does it need to be. No lost tech. The precision comes from skill, time, and organization. Stone hammers, levers, ramps, scribing, and vast coordinated labor. No iron tools, no mortar, no wheels for heavy haulage, clamps and mortar. The visible faces don't use metal clamps or mortar. Want this turned into a short article, a social thread, or a video script with beats and visuals? Tell me your format and length and I'll tailor it.